So this is a short video on the function of the ankle during walking. So the first thing we need to do to understand walking is to define a stride. So one stride is typically how we study walking. We can see a stride here is defined as heel strike of the same side to the subsequent heel strike on that same side. So we can see the right heel strike here to the next heel strike. And the important thing for us right now is that from 0 to 60%, we can see that as that foot hits the ground here at 0, that first initial contact, that same foot stays on the ground until about 60%. And then that foot lifts off. And so this part is what we're really mostly focused on for this talk, which is from 0 to 60%. And this is called the stance phase of gait. And so this stance phase is when the ankle muscles are actually stabilizing the limb and putting out a lot of torque at that joint. So let's see what that looks like throughout a gait cycle. And let's define the motion that's occurring at the ankle joint, the moment or torque that's being generated, and then let's talk a little bit about co-contraction, and then we'll move to a new variable we're not familiar with, and that's power. So let's start with motion. So we can see here on the y-axis, this is the ankle angles, and that plantar flexion is negative and dorsiflexion is positive. So, and this is 0%, 10%, 20%, 30%, 40%. And then we can see stance phase ends here. And so this is our stance phase motion that we get at the ankle. And so during a typical stride, at initial contact, the heel strikes the ground and then the foot plantar flexes just a little bit to make the foot go flat. This is foot flat here. And then once the foot is flat, there's a gradual progression into dorsiflexion to about 45%. We can see that represented here. The foot is flat on the ground, about 10%, and then the body continues to move over the fixed foot until we get to about 45%, and then the heel's coming off somewhere around here, and then essentially the foot starts plantar flexing rapidly during this last part of the stance phase of walking from 45 to 60%. Okay, so we have the motion of the foot during stance, and now let's look at the torques that are generated at the foot. So what we can see here is these are the net internal torques that are being generated at the ankle into dorsiflexion, which is positive, and plantar flexion, which is negative. And then here's our stance phase of gait here. We can see that there's a small dorsiflexion moment as controlling the lowering of the foot to the ground, and then after that, the foot's contact at the ground, there's this kind of gradually increasing plantar flexion moment to a peak around just under 2 Newton meters per kilogram. So from this we can know that the amount of torque necessary to walk normal is somewhere close to around 2 Newton meters per kilogram. And then we can see here the muscles that underlie these different moments. So for this dorsiflexion internal moment here, it makes sense that the anterior tibialis muscle is the primary muscle that can be associated with that torque. And then for the plantar flexion moment here, we know that the soleus muscle here can produce this torque, and then what's not shown is the gastrocnemius muscle. Okay, so that helps us understand the loads on the ankle, and then also what muscles are contributing to that motion. So let's now introduce a new variable called joint power. And joint power here is the joint moment, so this graph, times angular velocity. So that's the derivative of this graph. You can also think of this as the slope of this angular graph here. So joint moment here times the slope of this joint angle graph. What's part of why we're interested in understanding joint powers is it gives us an idea of how much work the muscles are doing at the joint. And it also tells us what type of contraction is occurring. So essentially a positive, so here's the power graph here. So positive values indicate a concentric contraction. Negative values eccentric contraction. And then 0 values isometric. And then the area under the curves represent how much work the muscles are doing at the joint. So if we kind of think about this for a minute, what we can see here is that the slope's important in determining power, and the moment's important in determining power. So what's really interesting here is we have this large moment here, which we know is going to contribute to a bigger power. And we also have this rapid slope, this kind of steep slope here, which is going to contribute to power. And notice what we can see here is this big burst with lots of area. So we know that there's a lot of work being done when this burst occurs. So let's study these different bursts and flat spots in the power curve. So let's talk first about this burst here, and we'll call it the A1 burst. So we can see here is that the foot is plantar flexing. There's a dorsiflexin moment, so the dorsiflexors are on, and so this is a negative power, which means that's eccentric ankle dorsiflexors. And then here at this space here is more isometric. And then we have an A2 burst here where there's some eccentric contraction from the muscles that are here, which are the ankle plantar flexors. So the ankle plantar flexors are controlling the dorsiflexion that's occurring here. And then there's a quick reversal of that right at this point here. So right when the slope here is 0. And then it switches to this would be A3, the A3 burst here, which is a large concentric power. And so what we can learn is that this concentric power is part of a stretch shortening cycle where we have isometric and then eccentric kind of muscle actions followed immediately by a concentric action. And so there's the potential for tendon recoil to contribute to this A3 power burst.